Everyone for being here. My name is Randy Ellingson. I'm here at the University of Toledo and part of the project Renewable Energy and Water for the U.S. and Serbia. And thank you very much to the sponsors of this international cooperative project, which the sponsor is the U.S. Department of State through the U.S. Embassy in Serbia. And yep, again, thank you all for being here. I will talk today about photovoltaic system design. And this is really intended just to give an overview and offer some insights into the kinds of information that are needed and the kinds of considerations that must be taken into account when designing and building and to some extent operating a photovoltaic system. The pictures that you see here, this is a photograph of an array that's about 335 kilowatts. That's referring to the DC nameplate capacity of the array. So if you look at all of the modules in the array and add up their specified power factor, it equals, in this case, about 335 kilowatts. And you'll notice in this photograph that some of the panels look a little bit different from the other ones. It's a little hard to see them because the shot was, smaller and taken from a little ways away. These modules were donated to the University of Toledo by First Solar, which is the US's largest photovoltaic module manufacturer. And they come from a variety of, they come from two different categories with regard to anti-reflection coating. So some of you may know about anti-reflection coating. It's on eyeglasses commonly, and it can be used in picture glass, especially in museums. But some of the manufacturing uses anti-reflection coating and some does not. That turns out to be a preference of the end user or the buyer of the modules. The particular modules that are used here were never sold commercially. They were instead Series 5. They were started as a commercial product, but they never sold any, and they moved on to their Series 6. On the right-hand side here, you can see in small form the output from a web page that monitors that solar array, and this shows generation for the last 11 months plus part of December over here. So I'm going to go ahead and go to the next screen. And just remind us that we're talking about an avenue for generating electricity that relies on the sun and photovoltaic technology, and the output directly is electrical power. And there are some components in this PV array, and I'll be talking about those today. The conventional way to generate electricity has been through various ways of generating heat, and to use steam to run a turbine, and that turbine then generates electricity through an electromotive conversion, which is really the opposite of an electric motor. And similarly, of course, you can use wind or hydro to drive a turbine and generate electricity. PV is different. So, okay. And also just a reminder that for both Belgrade and Toledo, the two homes for this project, we are, in terms of clear skies, we're in about the darkest time of the year. So things will start to improve a little bit in February and considerably more in March and April. And it turns out that at least here in Toledo, the best days for generating solar electricity are actually in April, late April, early May. That turns out to be the time of year when, on a good clear sky day, the skies are very clear and the sun can be quite intense. Okay, so just a reminder of where we've been in terms of our presentation schedule. We got started with an introduction. We heard about the importance of sustainability in our energy infrastructure. Ivana provided us an initial introduction to photovoltaics, upon which she will build next semester after the new year. We heard a really excellent talk from Professor Isalovich on water sustainability, and today here we are, December 15th, to talk about photovoltaic system design. Okay, so here's an outline of my talk on photovoltaic system design. Talk about the benefits of a solar PV system, what kinds of costs go into constructing a PV system or a PV array, how you can choose a good site for an array. And this, of course, depends a lot on the size of the array and the scale of your project. Just an overview of some of the engineering requirements. This is not an exhaustive address on these topics. A mention that for many projects, there will be a request for proposals for who will be installing, for example, a rooftop array, or who will be building the ground-mounted array, the components that go into an array, how you select and configure these electrical components in particular, how you can make a prediction on how much electrical energy you will generate, because that is where the value from the array really comes. And it's really important for financially modeling your array and determining whether your project is affordable at the prices that are offered in the proposals, for example. Very short piece on interconnection. So just a little glimpse into what's required to interconnect a PV array to the grid, the importance of monitoring, and then how arrays behave over their lifetime, and a little bit about what we can expect in terms of maintenance and operation. Okay, so benefits. Clearly, clean energy is a key benefit of solar PV systems. This is a low carbon technology. It's not zero because there are fossil fuels that are combusted and converted in the process of making solar PV. Well, if you start from the beginning, all of the materials, the mining operations, these all take energy, and a good part of that energy is going to be fossil fuels. So that energy gets counted in as an energy cost, if you will, to fabricate the photovoltaic system. And so photovoltaics is not a zero carbon technology. And if you look carefully at different energy technologies that can generate electricity, it turns out that hydropower is considered to be, or understood to be, a very low carbon impact. And beyond that, wind and solar are also low carbon impacts, but not as low as hydro. And the worst, as you might guess, is coal. And about 50% better is combusting natural gas. And then there are many others that come into play as well, many other energy technologies. Okay, so when I say predictable energy generation, that's really on kind of a slow time scale. So we know that photovoltaic systems respond essentially instantaneously to weather. You can mitigate that a little bit or somewhat considerably, by installing energy storage facilities that can be partnered with a photovoltaic array. But the energy generation is actually highly predictable over the course of months, and especially year by year. And we'll talk a little bit about that. There certainly are fluctuations in weather from year to year, but it's possible, for example, to evaluate a minimum energy generation for the course of a year, which has a 90% probability of being achieved in any given year. So that's where the energy generation is predictable. And solar systems actually have long lifetimes. Right now, you can plan on a solar array lasting for 25 or 30 years. The industry is moving closer to a 50-year lifetime, including 50-year warranties on the photovoltaic modules. Other components in the array, meaning, for example, the inverters, may need maintenance or replacement over that time frame. But the goal is to produce power over a half a century, and potentially more in the future. So a solar PV system isn't automatically cost effective, but there are many places where it is very cost effective. Ohio does not happen to be one of those places, and it's less because of our solar resource, which is fairly good, considerably better than Germany, for example, and Germany has a lot of solar installed. Our solar resource is definitely not as good as that you would find in the American Southwest or even the sunnier parts of Serbia, I believe. But the reason that solar in Ohio is not so cost effective has more to do with the low cost of electricity. And I actually would like to understand more about how the prices of electricity are determined for different regions in the United States and to some extent in the world, because here in Ohio, the cost of electricity is maybe something like 8 cents or so per kilowatt hour. And about 45 minutes from here or less in Michigan, the price of electricity is twice that. So clearly, there are some policies at play here that determine these costs. And in a place where electricity is more expensive, solar will become more cost effective. Solar systems are nearly silent. My aunt and uncle had an array when they lived in Colorado, and they really love the fact that it just sits there and does nothing and doesn't make any sound. When you get into the details, so most large scale, utility scale solar arrays that are installed now use single axis tracking to improve the energy yield by changing the angle of the photo module or the PV module as the sun tracks across the sky. You can hear those if you're close by. They make some sound. This, of course, can be measured and quantified. And power inverters that convert the DC electricity to AC electricity for coupling with the grid also make a little bit of noise, but again, this is pretty modest. Solar PV systems are distributed, so you can build these in almost arbitrary locations, depending on whether you're talking about ground mount or building mounted or carports, for example. And so there are benefits to having decentralized power sources where, for example, if you don't have distributed energy generation, then you're reliant, on, and there's a significant problem at the power plant, then, hundreds of thousands of customers may lose electricity all at once, whereas if you imagine a decentralized model where you've got different, solar arrays all around the city, then if the grid is designed correctly to be able to use that model, you can expect to continue having power, certainly at least during the day. Okay. So talking about costs, there's this acronym here, LCOE. I'm not sure how many of you may have heard of the LCOE, but it stands for the levelized cost of electricity. And it really is a sum of the costs over the lifetime of in this case, the energy plant, which could be a solar array or it could be It could be a coal power plant. And in the denominator is the sum of electrical energy produced over the lifetime. And those of you who are attuned to maybe financial models and the cost of money will notice that in each of these sums over n years, where you have initial costs, maintenance costs, fuel costs, you also have a discount rate, R, which is taking into account that money today is actually worth more than money in the future. So, if I could get you to just give me $1 million, and I told you I would give you that $1 million back in 5 years, I could make some money with that $1 million and then pay you back in 5 years, and I'd be happy to do that. But that just reflects the fact that money today is worth more than money tomorrow. And similarly, because energy costs money, energy today is worth more than energy tomorrow. And so there's this discount rate that says that in the future generation of energy is going to be reduced in value when you're evaluating this levelized cost of electricity. So if you think about year one, the year one costs for a solar array are, the investment in the land, if you have to buy the land, investment in all of the equipment, all the solar modules, the inverters, the cabling, the labor to install the array, any additional permitting costs. And the later year costs are going to be associated with M&O, which stands for maintenance and operations, monitoring the array, repairing the array, cleaning if that's something that's needed. If you just contrast this a little bit with what it would look like if we were building a coal power plant, then we would have input costs for fuel. We would certainly still have maintenance costs, and this would be a very different picture, right? Where the cost of the fuel, for example, can change year to year, so you don't really know. In this case, the fuel is really free, as long as you build the array in a location where someone's not going to put a tall building up and block your access to the sunlight. Okay. So in the case of site evaluation, there's a lot that goes into this in terms of certainly energy modeling. So, for the particular location on Earth, how much solar energy do you expect to receive from the sun over the course of a month or a year, throughout the year? There are also, many other aspects to consider. So this picture on the left here is just one of the buildings at First Solar's manufacturing plants, of which there are many buildings. And this is it here in Perrysburg, Ohio, 5 to 10 kilometers from us. And you can see they have a lot of rooftop solar that they have installed over the years. And I think they have about 2 megawatts the last I heard, though they very well could be installing more. And on the right here is just a picture of, a well-manicured farm field, perhaps somewhere in California, I don't know. So rooftops are a possibility. Only certain technologies go there now. And the reason I say that is that the way First Solar is making their modules, they're making them really specifically for utility scale. That's something that just changed over the last 2 or 3 years when they went to a larger form factor. Silicon modules are a little more interchangeable between rooftops and utility scale. And for those of you who are, interested in the technical difference or reason that First Solar's new modules are not compatible with rooftops, this has to do with the voltage that the modules use, which is a higher voltage than silicon tends to use. And it also has to do with at least in the US, our national electrical and fire code for rooftops, which requires that a solar array installed on a roof be capable of what's called rapid shutdown. And rapid shutdown involves de-energizing the panels on something like I don't know, maybe a 15 or 30-second time scale. And it turns out that making the power electronics that you need to do that with these higher voltage modules is challenging. And so if it's possible, they will do it. More likely, First Solar will, either just remain outside of the rooftop solar business for now, or potentially can reconfigure a product for rooftops. But there are other manufacturers of cadmium telluride who are interested in the rooftop business as well. Load implications just refers to the weight that's going on the roof. So you can imagine if you have, an old barn in the country, for example, and the barn is, made of wood, and you may not want to put solar panels on the roof, which uh, adds weight to the roof, and certainly solar panels can add force under windy conditions as well. So there's a lot that goes into evaluating the suitability of the roof. So for farmland, I was involved a little bit in a proposed solar project that was taking place in an agricultural community here in Ohio. And it's interesting how the company that wants to build the array goes about, doing this. They need to take into account their location, because they're going to need to be able to install transformers and connect to transmission lines, and they may need certain types of voltage switching technologies that are, or stations that are reasonably close by their array. But what they'll do when they find a place that they want to build is they will go, sort of knocking on doors of people who live in the area and own land in the area, and they'll contact these landowners and ask them if they would be interested in leasing the land for photovoltaic system use for 25 years, for example, and they establish, they make an offer to these people for the reimbursement that they will receive every month or every year. And it turns out that at least for many systems here in the United States, those lease rates are higher than a farmer growing agricultural crops and food can afford to pay. So you're looking at somebody who owns land agriculturally, and they're all of a sudden deciding, you know what, I think I like the solar idea because I make more money that way. So the other people in the community who are probably, in the agricultural economy are not happy about this, because it's going to drive up the cost, right? It's going to reduce the availability of land for agriculture, drive up the costs for agricultural land leases, and also reduce the amount of agricultural, sales in terms of things like tractors and fertilizer. And so it's a real issue and concern that's happening when these solar arrays are built in a typical agricultural community. Now, certainly there's interest in using what we refer to as brownfields, which could be, for example, a landfill where trash has been taken for years, and there's kind of a big mountain of trash, and it can be sealed and covered with dirt, and grass can grow there, and solar arrays can be installed in those places as well. Or an old industrial park, for example, where maybe some industry has, unfortunately, and well, at least historic, looking back, right, retrospectively, inappropriately contaminated the land. So that would be considered a brownfield where you would not want to build homes, but you could build a solar array. One of the things that we have here in Ohio is a program called Pilot, and I don't know the details of this. I believe it's a state program, but the solar manufacturer can be allowed to pay to make payments to the community instead of paying taxes on their electricity sales to the state of Ohio. So this is something that the communities like, right? Because you can find communities that don't have maybe a huge tax base, so maybe they don't have as much money for their schools as they would like, but now you have this influx of money from a large solar plant that could be tens of millions of dollars over the course of the array. So that's another, maybe one or $2 million per year coming into the county or the city's budget that could be used for schools and other improvements. So that tends to be a good thing, but there is a lot of disagreement about whether or not people want solar in their community, and there are many jurisdictions here in Ohio and Michigan where people vote to say we're not allowing solar at all in our county or in our jurisdiction. So it's just an interesting problem that way. Um, so here's a little glimpse into the engineering requirements. The array that I showed on the front page, on the title page, these are some of the drawings that have to do with that field. So you can see if you can see here, it's phase 1.34 acres of land. The number of modules changed a little bit to 936, I believe it is. And what's shown here is this is a parking lot, this is a field, this is a pond. This is an electrical substation. There are train tracks right here. This right here is actually a tunnel that was pre-existing. And so, what has to go into consideration, excuse me, there needs to be a land survey. It's possible, depending on the amount of undulation that you have and contours of the land, that you may need to do some flattening to optimize your energy yield. That, however, disturbs the soil, which brings me to the second bullet, which has to do with the geotechnical and soil survey. So you need to know that the soil is not going to be corrosive. You need to know that the soil is stable, and that your mounting posts that are driven into the ground or drilled into the ground are deep enough to provide you with stability over the lifetime of the array. It's hard to see here. There's a title block of text over the top, but you've got multiple rows of solar panels here. So you need to take into account how to space those, what the tilt angle will be for the module, which direction the modules will face. And you certainly need electrical drawings, and ultimately there is also some evaluation that takes place for grid impacts. So I'm going to click through a few other drawings here, I think. Let me see here. There we go. This is just a little detail from the geotechnical soil survey that was done. You can see it talks about moist, stiff, gray-brown, sandy, lean clay with trace of gravel. So they put these cores, they did these cores, I think, at 4 different locations in the field and evaluated the soil. So there was a cost for that, maybe $4,000 or something. This is an early diagram of the field showing the individual modules. There's some text on here that identifies the different modules. It's difficult to see at this scale, and actually the way the array was built, this was modified slightly. There's some detail here that shows some of the racking and the tilt of the solar panel and the spacing between the rows at a tilt angle of 25 degrees. And what they show here is that they chose this based on the sun's angle on its, when it reaches its lowest point in the sky, which is around December 21st, coming right up. And they're showing that basically one row is not significantly shading the neighboring row. So That's nominal. If you looked carefully, I think there might be a tiny bit of shading depending on, again, how flat the land is, for example. Okay, so next is request for proposals. So this is actually from a different project, a much smaller project. This was from about a 47 kilowatt system. And this happens to be a document that was prepared for a nonprofit organization. Let me keep an eye on the time here. And let me see, I'm gonna, for some reason, it won't let me click on that link. Back to the, I don't want the laser pointer. I'm gonna click on this link, see, okay, so I think you can see my screen, right? So this is the request for proposals that I was referring to from 2017. And, there's a short description of the project. There's information about the arrangement of the electrical system. There's some discussion of how the financing will be handled, qualifications and standards. There's a requested timeline for making the array operational. There are guidelines to how the proposals should be prepared, et cetera. So I'm going to stop with that and go back to the presentation. Okay. So the system components that come into play, I guess I was a little bit quick switching to the laser pointer. I can't see it. There we go. Photovoltaic modules. I'm just going to show you. This is back to the University of Toledo 335 kilowatt array. So here are these. Here's the data sheet for these modules that were never sold commercially. I don't know how much they made. I think they made more than a megawatt. I don't know where they all ended up, but we got some of them, which is great. And there's some overview information here about the technology, and then there's information about the different First Solar Series 5 modules based on their rated output power. So you'll notice here that, well, actually, I'll go into that later. So these are standard test conditions. This is normal operating cell temperature. So these are conditions that are closer to the operating conditions of the array. And there's some temperature characteristics. And of course, there's information about the size and the thickness and what kinds of connectors they use and the cell type. It says here they use up to 798 cells. This is a unique product. If you can see down here in the corner, they actually had 3 different pieces of glass that were glued to these metal unistrut rails and interconnected with each other. So their Series 5 plan was to make a larger module out of smaller modules. And this is the plan that they scrapped. They said, we changed our mind. We're not going to do that. We're going to go straight to a larger piece of glass. And so that's what they did. There are inverters as well. So these are the technology that converts the electricity from direct current to alternating current. And if you look at the data sheet for the inverters that we ultimately used, these are from Yaskawa, which I think may be maybe a Korean company. We're using the PVI 60 TL, and TL stands for transformerless. Again, there's just some overview information on the first page. And then on the second page, you get into the detailed specifications for the DC input from the solar array, the alternating current output to the electrical grid and substation, the efficiency with which the electrical energy is converted from DC to AC, and then a few other considerations, including the warranty you can see, which is 10 years, noise information, and so on. Okay. So, and then that leaves us basically with the BOS, which is balance of systems. And that includes the racking, so how the modules are mounted and how the inverters are mounted. Although there are many more photovoltaic modules, 936, than there are inverters. There are 6 inverters on this system. Cabling, there's the transformer itself that we had to purchase and install. There's monitoring hardware and networking hardware, and then there is a meteorological station that was installed but has not been connected to the network yet, unfortunately, partly because our university has some really, they make it very difficult, basically. So it takes like 10% of my time or something for, a year to get that working, it seems like, but I'm going to try to get an undergraduate student to help with that soon. Okay. All right, so array selection, I'm sorry, component selection and configuration. So this is part of the presentation where I could have gone into more detail. I just didn't quite have time to present those or present the slides. So a solar array consists of strings of modules, and a string is just a number of modules that are connected in series. And so if you consider, for example, these are 2 AAA batteries. If you connect these batteries end to end, then instead of being about 1.2 volts from a single battery, the voltages will add. You'll get about 2.4 volts from 2 batteries in series, and you can just build up more and more batteries. Here's a double A you could throw in. You get 3.6 volts. So the same thing happens with solar modules in series. The voltages add, and then you are left with a single string of modules, and the current from that string will depend on the current from one of the modules, because the current is determined just by the weakest battery or module, in this case, in the string. Then if you have these, if you have, for example, 2 or more strings of solar modules, and you connect those in parallel, so imagine you've got 2 more batteries here, and you connect these ends together and these ends together, now the voltages will stay the same from each of these strings, but the currents will add. So you can build up the current by connecting multiple strings in parallel. That's what's indicated here. So the inverter that you choose then will have specifications for the maximum voltage and the maximum current values. And you can see here, for example, the absolute maximum input voltage, 1000 volts DC. The maximum, let's see here, the maximum operating input current, 114 amps. The maximum potential or available PV current, 204 amps. Okay, so it turns out that each of these inverters has 3 of these maximum power point trackers. Those will adjust the current and the voltage at any given time to optimize the amount of power produced, because power ultimately translates to maximum energy, and that's the goal of any solar array. You can see there's also like a minimum starting voltage. So when the sun is coming up in the morning and you start to get a little bit of light on the array, it's pretty quick. The voltage rises pretty quick at low light intensities. So the array will start pretty early, even when it's generating relatively low power. Yeah, so let's see. I think we looked at that data sheet already. Let me see, is this for the, yeah, okay. So I'm going to go on to the next slide. And so when you're considering the modules with regard to the inverter, I just mentioned that there's a maximum string voltage or input voltage, and that's 1000 volts for these particular inverters. So then you can go down to your module parameters and look at You actually want to look at the maximum voltage is going to be the voltage at open circuit. In this case, it's about 217 volts. And so just by doing a little bit of math, you can tell that 217 times 4 modules in series is still less than 1,000 volts. But if you add a fifth one, then you'll exceed that 1,000 volt maximum. So you can have 4 modules in series for one string, and your maximum current for that string would be the current of a single module, which is 2.25 amps. And so I just want to point out here, these module parameters are specified at standard test conditions, which means 1,000 watts per square meter of sunlight energy, which, very roughly is going to be the amount of energy incident on a surface that's pointed directly at the sun at solar noon on maybe not the most intense sunny day in Toledo or in Serbia, but a decent sunny day in maybe early spring or late fall, something like that. Depends on where you are on Earth, and obviously it depends a lot on the conditions for the day. But 1,000 watts per square meter. AM 1.5 refers to the assumed spectrum of sunlight, which doesn't change a lot, but changes a little bit with weather conditions. And then a module temperature of 25 degrees C, which is basically room temperature. So modules on a summer day will heat up considerably more than that. Okay. We go to the next slide. If you're actually designing one of these arrays and learn how to do this, you'll realize that you need to take into account temperature effects because photovoltaic modules behave very differently at very cold temperatures to very hot temperatures. There can be significant differences in their efficiency of power conversion and therefore in the output powers. Voltage changes, it rises at colder temperatures than the standard test condition 25C, and at higher temperatures, it decreases. So if you're concerned with maximum voltage, you need to take into account the range of temperatures for the extreme temperature limits for the location where you're building the array. Similarly, but really in the opposite direction, this should be I sub SC. The short circuit current will increase when the module heats up. That has to do with the semiconductor band gap effect primarily. Although it's true for silicon and for cadmium telluride that the band gap energy decreases with increasing temperature, it's not so clear that that's the same case for perovskite, for example, which is another technology that people are working to commercialize. So you need to take into account, the hottest temperatures as well when you're looking at the maximum currents that are allowed. And these temperature coefficients are going to be provided on the module data sheet. And so that's where you can go to do these calculations. So you're definitely going to want to have an idea of how much energy your array is going to generate. And if this array is for your home, for example, or for a commercial business, you'll want to know that you're generating, as much energy as you want, but perhaps not more than you want, because you may not be able to sell the power to your neighbor or back to the power company. And so you may want to limit the size of your array somewhat. And so that entails understanding how to predict the energy generation in kilowatt hours or megawatt hours or gigawatt hours, depending on the size of your array and the time scale, maybe month by month or over the course of a year. And this is going to depend on the local solar insolation. So this word right here refers to the intensity. So the energy intensity. So the kilowatt hours of sunlight per unit area, which is actually not written in the slide here, but per unit time, for example, per day, per month, or per year. The energy that you will generate also depends on the array's what's called the nameplate capacity, which is if you add up the power capacity for all of the modules in the array, that's your total DC power at standard test conditions. It'll depend on the array's orientation relative to the sun's path. So, for example, the elevation angle will change how much energy you'll get at any given time and day, and the azimuth angle. So, here and in Serbia, if you want to generate the most energy, you're probably going to end up with your array pointing very close to straight south. That can change a little bit depending on whether your mornings or afternoons are sunnier throughout the course of the year. And so you can run these energy prediction models as a function of the azimuth and the elevation angle to optimize your predicted power output. And so most of these programs will use something called typical meteorological year. So, what does a typical year look like in terms of the weather and the amount of sunlight that you're introducing? So there are these files, TMY3 data files that are available, I believe, for different locations throughout the world. I think the closest one to us is the Toledo Express Airport, which is maybe 15 miles away from us. And yeah, I mean, I know these exist for the US. I have not worked with TMY3 data sets, but there are other typical weather data sets available throughout the world. So here's a program called PV Watts to see where this is going to open. It's going to open on my other screen. So I'm going to bring it over here so that you can see it. So this is a calculator that's provided by the National Renewable Energy Laboratory, and it's just a simple calculator, as I will show you. So, I'll go ahead and put in Toledo. Actually, I'll put in our zip code, which is 43606. Oops, T in there. 43606. Go. It will, locate approximately where we are. It'll find a weather resource, so it has a latitude and longitude. And down here, it'll show a map of where, where it's targeting. And so the airport is actually just out this way a little ways along Interstate 90. We're here, and so I'm satisfied with the location. So I'm going to click this orange arrow, and then it asks for the size of the solar array. So, maybe I want to aim for something that, I can't really install solar on our house very cost effectively because we have a lot of big trees around our house. But if I wanted to go completely electric, and I had, money for an energy storage system, then I would probably want something like a 16 kilowatt array, which is pretty big and would cost a significant chunk of money, something like, maybe $50,000, or maybe I could get a better deal than that. The type of the technology matters, so there are some options here. I'm going to choose thin film, assuming I can use something like cadmium telluride or perovskite. The array type is going to be fixed rather than, for example, one-axis tracking. So I'll use roof mount. The system losses can vary quite a bit. I think I'm going to try to keep my losses a little bit lower than that, put them at 12%. That has to do with, you can click this information here and find all kinds of details about the losses that are modeled in here. The tilt angle for our roof is a little bit steeper, so I'm just going to assume that we're going to install these modules parallel to the roof without doing anything very fancy. So I'm going to say that's about 35 degrees tilt. And even though we don't have very much roof that's facing, actually our roof does not face straight south, it faces a little bit southwest. So I'm going to say 210. 210-degree azimuth, which is a little bit to the west of south. I'm going to leave the advanced parameters alone. I'm just going to click Go to Results. So if their engine is working correctly, it calculates the amount of kilowatt hours that would be generated. That's AC output, so alternating current over the course of the year. And you can see it does this month by month. And you can see that the amount of energy generated is going to peak in, it looks like July for a typical year. And it's going to be more than twice as much as is generated in December. So there's some variation month to month. Our energy consumption right now for electricity at our house is somewhere around 5,000 kilowatt hours. But we also use a significant amount of natural gas for heating. So if we wanted to say no more gas, we're going to go with electric, then we could say, okay, we'll have about 15,000 kilowatt hours per year available for, for heating, but that's over the course of the year, or for cooling. We do have an air conditioner in our house on the second floor. So this is just a way that you can get some initial results, and you can, print them out and use this as kind of a quick check. Okay. So if we go back to, let's see here, back to the presentation, PV Python is a more sophisticated energy modeling tool that I will talk more about in a later webinar. This one's much more, I think, global friendly in the sense that you can choose any location on Earth for your modeling. If you need weather data sets, you still have the issue of finding those, but there are companies that create weather data sets from satellite data, for example, and weather data is becoming more and more available, although people who do this for a business typically pay for their weather data. So PV Python. So PV is the key name here. It's a community-supported tool. It also exists in MATLAB, and it's used for simulating PV system performance. It's maintained through Sandia National Labs and something called the PV Performance Modeling Collaborative. And so if I click on this PV Python, let's see where it leads us. It's leading us to the other screen again. So I'll bring that over here. So this is a picture of the web page for the Photovoltaic Performance Modeling Collaborative. And, it has a lot of interesting information on what steps go into modeling energy generation. And of course, it has the PV Lib toolbox, which as I mentioned, exists either in MATLAB format or Python format. I teach a class here that discusses and introduces PV Lib for Python. And so that's something that we'll talk about in a little more detail in the future. Okay. So I mentioned that we would talk about interconnection. That's really just getting permission from the power company if you plan to connect to the grid. Sorry, I've got some typos here. I'll fix those before I make a PDF, but permission to install and permission to operate. And this is a pretty dry document, not that interesting, but here's a copy of the interconnection application for preliminary approval for looks like a 43 kilowatt system that was built in 2020 here in Toledo. And so there's kind of a cover page, and it looks like there's another PDF that was attached. There's just a letter saying that this company, Yellow Light, that planned to do the installation, that request was made to evaluate the proposed electrical drawings for code compliance. So that's something that has to happen here in the United States. They're the electrical drawings that are made available to the power company, and then they go through and evaluate the viability of the array and ensure that it's going to be safe to operate. So we're getting close to the end here. Monitoring of the array once it becomes operational is really critical to ensure that it's operating correctly. You can imagine that there are a lot of PV arrays, certainly here in the United States, certainly here in Ohio, probably all over the world that have been installed, and they may not be watched very carefully. And so potentially years may go by when they're not operating correctly or maybe not operating at all. And the people who bought the building don't know anything about the technology. And so, in some of those, worst case scenarios, certainly, many tens of thousands of dollars, maybe, of the opportunity to generate solar electricity can be lost. And so, I understand pretty well from just watching solar arrays, the one outside of our building at the university, and now my involvement with Glass City Community Solar, which is a nonprofit where we monitor, about a dozen, about 12 or so photovoltaic arrays in the community. Problems can happen with these arrays that will shut them down. And unless somebody's paying attention to, receiving and paying attention to some kind of alert or notification, then no one may know about it. So, what you really want is a monitoring setup that can detect problems and notify you proactively right away when these problems or potential problems occur. There could be a problem with the inverter, there could be a problem with a string on the inverter, and monitoring hardware, depending on the sophistication of what your goals are, those can also be require maintenance and calibration because you're talking about sensors for the intensity of the sunlight and potentially, the air temperature, the module temperature, things like that. This screen right here, actually, I can just click on this because I believe I'm connected to our VPN. So I can bring up the live monitoring of the array in front of our building. And you'll note, first of all, that so on the bottom axis is the date and time. Looks like we're monitoring over about 3 days, 3 days worth of data. And you can see in the bottom graph here, this is monitoring the solar radiation or irradiance intensity. That's actually on this axis, measured in watts per square meter. And on this axis, we're monitoring the array's AC power, so the power after the inverter. And what you'll notice, if you can see here, is that the array's AC power in red tracks pretty closely with the intensity of the sunlight, which is measured in white here. This green curve here, it says BOMI on the legend, is the back of module irradiance, and that really is a pyranometer, which is the name for the instrument that measures the sunlight intensity. That's pointed downward from the back of one of the panels. These panels do not work bifacially. They do not generate power from the back, but we're measuring that power anyways. And you can see here that Dragon was telling the truth. We got a little bit of sunlight today. At the moment, you can tell by the POA, which is plane of array irradiance, that the intensity of sunlight is only about, maybe 1/9 of what it would be if it was sunny, or 1/8. And the AC power is also relatively low because this is a 31,000 watt array. So it could be, higher in the high 20,000s, but it's only down around 3,000 right now. In the upper panel, we're plotting the temperature of the air, which is the white curve, and the temperature of the modules, which is the red curve. And you can see that during the sunniest spell today, the module temperature just reached 25 degrees C, which as far as the temperature goes is the standard test conditions temperature. But in the summer, especially, and on a sunny day, these temperatures will reach as high as maybe 65 degrees C. And in hotter parts of the world and, you know, more intensely sunny parts of the world, it goes hotter than that, certainly. So, so we record these data. But one of the challenges, for example, is that the pyranometer that's measuring the plane of array irradiance through, I guess, a little bit of, you know, careful observation, I've determined that that is out of calibration. And so it turns out that it's not quite trivial to desolder. We don't have power out at the field for, you know, plugging in devices. So we end up using like a butane solder gun. And, you know, my job is not to keep this monitoring system running, although I've made it part of my job. So, but it's when I have time to, you know, enlist the help of some students, we can go out there and demount that pyranometer and send it for calibration and then remount it. So that's just the way things go. All right, so getting close to the end here. Maintenance and operation. So there's certainly a lot more I could talk about on this topic as well, but just to give you a little insight. So the array in front of our building is, it's not fenced in. It is a ground mount array. It's not up super high, but it's a relatively expensive array because it is up somewhat high, but it's easy to access. And we have had some broken modules, and at least in one of those cases, it looked like somebody walking by may have just thrown a beer bottle at it. And you know, these are glass modules, so they are subject to break. The university has another array on another campus that is close to some softball fields, and I know that in the past I've seen that there have been, you know, some baseballs or softballs that have hit the array and broken a module or two. Manufacturing defects can also lead to broken modules. And a broken module, depending on how bad the damage is, can break the electrical circuit within the module, which is really, you know, modules connected in series. And if you take a module down electrically, you can also take down a string. Inverters can blow fuses. And so, you know, monitoring relies on network and software reliability. So there are different things that may need to be repaired. Module warranties might be, you know, 25 or 30 years now, but inverter warranties are less than that, more like 10 years. There are places where modules need to be, you know, arrays need to be cleaned. These are places like desert installations where rain is very infrequent and dust can be high. So there are costs for maintenance and operation of an array. They're relatively low. I'm going to say, you know, for utility scale, they probably have this down to something like, think about this. I think maybe something like maybe $5 per kilowatt per year, $5 to $10 per kilowatt of nameplate capacity per year. All right, so my conclusion slide is underfilled, but just to point out that there are numerous details to understand. And thank you for listening, and I'm happy to take questions and we can discuss anything you'd like to discuss.
Thank you very much, Randy. This was a
Thank
great
you, Dragan.
talk.
Thank you, Randy. It was really nice.
You're welcome. Everybody's welcome.
Obviously, we have some time for questions, and it's kind of interesting to hear what you need, you know, to have a solar array or panel installed in a house, for example. I would ask a question that is more related to, you know, generating power, you know, at like you mentioned, like potentially actually you have some of those arrays in deserts, and I can imagine, you know, that they could be installed at some remote sites, such as, I don't know, mountains or old mining sites or something like that. Obviously, the question is, you want to have location of those arrays close to the place of usage, but then, like if you use those inverter that will convert to from DC to AC, is there potential to, like, what is the distance, for example, that you could efficiently use, solar panels from the, let's say, site of usage? Do you have any idea about that?
I believe for, a smaller scale power line to, I used to hear that it was something like $10,000 to run power lines for a mile, but that would be low capacity power lines like to a cabin or a home or something. That actually seems a little bit low to me. It might be much more than that even. So I don't know exactly, but I know that proximity to transmission lines, and then more importantly, making sure that the transmission lines have the capacity to carry the electrical power, really important. So.
Sounds good.
Randy, maybe I have one question. Thanks for
Okay,
the
Nicola.
interesting talk. In the end, I just came to one idea. I don't know, maybe you mentioned, but what is the risk from the hail on photovoltaic modules? Because I don't know in America, but in Serbia we often have some those large pieces of hail. And will everything break if it happens?
Yeah, that's a great question. So first of all, hail testing is something that's done by every photovoltaic module manufacturer. And I actually am not I'm not very familiar with the specification that's provided, but I have seen the testing facilities where uh, ice or some simulated, hail, I'll call them, pellets or larger size hail, can be fired at a known velocity to simulate the impacts of hail. And I think hail damage is pretty rare, but I think that in a really bad situation with a hailstorm, it could be catastrophic for an array. And so, when you're talking about one of these utility scale systems, they can cover, many tens or maybe even hundreds of acres. This is something that must be insured, right? Because the cost to replace those modules, really the biggest cost is labor. You have to cover that. So as far as, I believe that since, at least in the United States, residential and commercial roofs are insured against hail damage. Solar panels must also be insured against hail damage.
Yeah, on the big arrays, probably it's possible to prevent hail with some rockets or something. Like for the agriculture they do, for if it's something really important, then they can act to prevent it and not to do insurance. I don't.
Okay, I don't know how they could prevent it, but okay.
Oh, well, I don't they just put some like meteorological rockets which explode and prevents it from falling. As I know that we have those stations in Serbia in parts where there are a lot of agriculture, but in parts where they aren't, that don't exist.
Okay, I don't know. I'm not familiar with that, but
yeah, that's right, Nicola. I'm aware of those. Now, obviously, you rely on others, to prevent those events, and I know that some of the agricultural producers of fruits, for example, because many times they're, for example, raspberries or blackberries were damaged by hail. They actually, instead of that, they use like a tiny mesh, like put over their plants. So Seems
Mhm.
like
Difficult.
the whole system of preventing those type of hail events may not be suitable for, depends on timing, I suppose, and ability of those rockets to hit the clouds, that would bring hail. But yeah, that's kind of interesting concept that you mentioned.
Yeah, that's point. Okay, then if no one else, I have one question, but basically it's not more the question. I would like to hear your maybe opinion concerning. Sometimes I listen many times on the television and in speaking with different people. So sometimes people basically complain. Usually when they wonder they should install something like a solar system, solar panel on the roof, especially in the homemade atmosphere. So they usually wonder, they sometimes hear, that concerning the cost which they have, when they install something like that in the house, in the roof, and then also the life of the solar panel before they have to, replace. Then sometimes people just complain, that basically when it's coming the time that they basically return the money which they give for the installation and everything else. Basically, it's very quickly also and the time to replace the new solar panel, or something like that. So I would like your comment in the concerning that aspect. What do you think and what kind of are your experience? And also, I mentioned in some of my talks, for instance, that in a purpose, one of the way to basically increase the possibility that we get electricity from the solar panel, it's to use basically the higher surface and more of this solar panel. Just we need more spaces. And concerning, I'm not asking concerning the silicon, because the silicon is one of the abundant element, but I'm more interested, for instance, from the point of cadmium telluride. How much, because it's rare semiconductor, and concerning all of this, so how much of that it would be possible to use, for instance, cadmium telluride, if we want to really replace energy, or to really use the solar panel, not only for the small uh, replacement of the whole renewable energy, even to increase the percent.
Okay, so thank you, Ivana.
I
So I
mean,
think I heard a couple.
yeah, just your comment, your opinion. And
Yeah, I think I heard a couple of questions, and I heard a couple of questions in there. One has to do with sort of the general question of whether or not it is advisable to install a solar array on your rooftop, taking into account things like the cost and the reliability of the technology and how long it can last. So I'll start with that question. And I think it's my opinion that uh, you know, so first of all, if someone decides they really want to have solar on their own rooftop, it would be really important to know that they had, recently replaced their roof covering. In this case, there are a lot of people who use something called composite shingles here that have a lifetime of 25 or 30 years, expected lifetime. You don't want to put a solar array up and then have to replace your roof 5 years later. That would be inconvenient and add additional cost. You also, I think that in, today's technology is reliable. So if you have an installer who has done their homework, they can choose modules that will last for 25 years. However, the solar array is not going to be maintenance free. you're likely to have to replace at least one of those modules over the course of the lifetime, and maybe several. So there's some interesting questions there, because modules that were made and installed 10 years ago, those module designs are typically not available anymore. So if you do need to replace a module, it can be difficult to find one that's compatible. As far as as far as the inverter goes, those are likely to have to be replaced during the course of the lifetime of the array, but that's okay. But it's something you should plan for. A cost of something like maybe as much as about $500 per kilowatt of capacity. The other thing I'll say, though, is that I think it's a much better model for most people, if there's the possibility of using community solar. And by that, in the United States, what that means is, if community solar is allowed in a particular state, that means that someone can build a large solar array in a centralized location, and then basically sell like a fraction of the array to an individual homeowner. Then as this solar energy is generated at this large array, some fraction of that energy is credited through something called virtual metering to the bill of the homeowner who owns that fraction of the community solar array. And what's good about that is that it can be a ground mount. It can be, maintained in one location by a professional company, and you end up with a lower cost of ownership and the same benefits to society. And so here in Ohio, we do not have the community solar policy. And the reason for that most likely is that the investor-owned utilities, the big power companies, they don't really want people to be in the business of competing with them. So they have talked to our policymakers, which is the Public Utilities Commission of Ohio, and told them, no, please do not do that. And so unless our lawmakers decide to do that, it won't happen here in Ohio. It's happened in quite a few other states, but not in Ohio. So your second question has to do really with the scarcity and availability of tellurium, and how that could impact the ability for that technology to expand in the future. And recently, the University of Toledo hosted the sixth annual cadmium telluride photovoltaics workshop, and we had two people speaking on that topic. We had a professor from the University of Utah, I believe it is, Mike Moats, and he's an expert on mining recovery of elements and availability of elements. And we also had a speaker, Sarah Hayes, I believe it is, from the United States Geological Survey, and she is also an expert on critical elements. And so the primary element of interest for the cadmium telluride community is indeed tellurium. And I can say something about that, but there are other elements that are important to the technology as well, like indium, like selenium, for example. And these are elements that could also influence the cost. So the way tellurium is recovered now is it's recovered as a byproduct, primarily as a byproduct of the copper mining industry. And it turns out, based on the information that was presented and people's best understandings, that we as a society and the industry is not very good yet at capturing tellurium from the waste products of other mining, and it's not really possible. It's because of the way tellurium exists in geological formations. It's not possible to go mine tellurium. So you always have to recover it as a byproduct. But it turns out that there is an opportunity to increase the supply of tellurium just through better technology, and sort of better at people being better at paying attention to the desire to capture the tellurium. Just by changing our technology, we can probably increase the tellurium recovery maybe by a factor of 3 or 4 or 5, or even 6-fold, maybe 10-fold. I'm not sure exactly, but somewhere around there. So, but to get more to your point, I think that people don't really know exactly how well that industry can scale. First Solar is a big company and probably one of the biggest users of tellurium. And one of the things that they are interested in, and that actually aligns with their plans to introduce a bifacial product, is to make their absorber thinner. And so if they make a thinner absorber, that will use less tellurium and enable them to make more watts per kilogram or more kilowatts per kilogram. So I don't think that we're bumping up against any walls right now in the tellurium supply, but your question was a good one. What happens in the future? First Solar and others.
And in the point of industry, because I'm not so much familiar with getting tellurium from copper, but I think it's not real clean technology of getting something like similar as a silicon, which the silicon also production of monocrystalline silicon is not also really clean, process of.
Right. So I can tell you that the energy intensity for silicon is much higher than it is for cadmium telluride. And that's because of the energy that's required to break the silicon oxygen bond to purify the silicon. I think that so if you look at, so mining, right? Mining in general is a dirty operation. Tellurium is recovered as a byproduct of waste, the waste stream from primarily copper and maybe potentially zinc mining also. Very good question. Could talk more about that in the future. Actually, there will be, I anticipate posting slides on that topic from the workshop, but I still need to go through and get permission from everybody, and then they will be posted, and I can point you and others to that resource. So, yeah. More questions from other people? Any other questions?
So, Randy, maybe I can ask one general question. So it seems like technology to produce photovoltaic arrays is present, and expertise is here. The question is, what will bring the cost down, like especially for residential? And you mentioned a couple potential solutions, like an array owned by city or town, like a central array. But in your opinion, what will bring the cost of residential solar panels down?
So the component costs have dropped considerably over time. Certainly longer ago than 10 years, and definitely over the last 5 to 10 years. They won't go down every year, but one of the things that can help drive costs lower is increasing efficiency, particularly of the solar panels themselves. Solar panel efficiencies in practice have gone up from roughly 14% in maybe 2005 or 2000 to 2005 to now averaging close to 20% or a little bit higher. People are working on technologies that can increase that efficiency towards 30%, but this probably is something that will take another, maybe 5 to 10 years to happen. So those costs will decrease. A lot of the costs are in what are referred to as soft costs. So, to some extent, like the cost of getting permits, how difficult it is for the installer to get all the paperwork done, interconnection agreements. And so the U.S. Department of Energy is working on streamlining these processes to make them easier and quicker, and that will help to take some costs out as well. I think that on the residential rooftop scale, it would be a little surprising for costs to come down, 50% in the next 5 to 10 years. And that's mostly because a significant portion of the cost is labor, and it's just a little bit difficult unless you are talking about, uniformity of your structures to imagine that you can do a custom installation for significantly less labor than is used now. So I don't think costs will continue to decrease because technology is improving and efficiency is improving, so you get more power per unit area. But certain costs are going to be a little bit stubborn to drop a lot. So at the utility scale, costs are already pretty low, and they will continue to drop.
Thanks.
Yep, you're welcome. Okay, well, it's 1:30. I'm going to stop the recording now. And